Hey, Hui,
Hey, hello, Joseph.
do you want to play a game?
Okay, sure. What is this?
Okay, let me show you. Okay, this game is called a Chomp. Chomp is a two-player game in which players take turns choosing a square box from an M times N board. The pieces above and to the right of the chosen cell disappears after every turn. Then the players take turn. The cell on the bottom left corner is considered poison, so the player who is forced to choose the poison cell loses.
Okay, I roughly understand the game now, but can you start first?
Sure, no problem.
How come?
Let's try again.
Okay, now I really know how to play already.
Yeah, let's try 2x4.
Okay, you start first.
Okay.
Wow, how come like that one?
Okay, I give you a chance. Let me choose a dimension. Is okay?
Okay. I want 4 times 4.
Okay, one lah. Okay.
Okay, you can start first.
Okay, sure.
Chomp belongs to a category of impartial two-player perfect information game. For any rectangular starting position other than 1 times 1, the first player can win. This is due to a strategy stealing argument created by John Nash in 1949. The strategy stealing argument goes like this. Assume that the second player has a winning strategy against any initial first player move. Suppose then that the first player takes only the bottom right hand square. By our assumption, the second player has a response to which will force victory. But if such a winning response exists, the first player could have played it as a first move and thus forced victory. The second player therefore cannot have a winning strategy. In the game of Chomp, the player who moves first will always have a guaranteed winning strategy. However, except in the smallest and simplest games, no one will know which first move will lead to the guaranteed victory. In a game of 1 times n Chomp, the winning strategy is simple. Remove all but the poison piece and player 2 will lose. In 2 times n Chomp, the first player has to remove the top right piece such that the top row will have n-1 pieces and the bottom row will have n pieces. No matter what the second player does, player 1 will be able to maintain the pattern of n-1 in the top row and n in the bottom row. This will result in player 2 having no choice but to leave a minimum of 2 pieces, the poison piece and a safe piece which player 1 will obviously pick. For n times n Chomp, player 1 removes all the pieces but the left and bottom edge. Whatever moves player 2 makes, player 1 only has to copy the exact same move on the opposite side to maintain symmetry. Because of the symmetry, player 1 will always have a move to make that doesn't involve taking the poison square. Chomp with 3 or more rows have resisted comprehensive analysis. Computational methods have identified the winning first move for thousands of specific array shapes, but they have failed to reduce the game to any simple formula. Here are the winning strategy in a few 3-row Chomp. The winning strategy of 3 times 4 Chomp is to remove the top right 4 pieces. Whatever player 2 does, player 1 can then reduce the geometry to that of the winning strategy for a 2 times n or n times n Chomp. Here, by removing this piece, the 2 times n winning strategy can be observed. Similarly, the same strategy can be seen vertically here. In 3 times 5 Chomp, removing these 2 pieces is the winning strategy. Here, player 2 reduced the geometry to an n times n board, which player 1 can then use the n times n winning strategy. If player 2 removes the pieces such that the player 1 has a 2 times n board, he can again reuse the 2 times n winning strategy. As you can see, any other moves will reduce the geometry to that of a 2 times n or n times n configuration that player 1 can then abuse. In 3 times 6 Chomp, the winning strategy is to remove these 6 pieces. Once again, any moves that player 2 does will make a familiar geometry that player 1 can then manipulate to a simpler winning strategy. In the past few years, 3-row Chomp has been studied in detail by Doron Zellberger and his students at Rutgers University. They have found no concise formula for winning, but the distribution of winning and losing moves is not random, and there are strong regularities. When laid out in an XYZ space, the winning strategies should tell if there is indeed a concise formula. If it was scattered completely at random intervals, the game has no ordering principle. However, if there is some simple rule, obvious patterns would show up in the distribution of winning points. The distribution of instant winner points start out looking random, but then seems to become ultimately periodic, with either a constant value or a simple repetitive pattern. The ultimate periodicity of the sequences was later proved by Stephen Bryans. The diagrams reproduced here, courtesy of Eric J. Friedman of Cornell University and Adam Scott Landveld of the Claremont Colleges, show instant winner positions for certain 3-row games. Blue points are instant winners, 10 points are not. The diagrams are slices through the XYZ volume, the larger panel along the plane where x equals to 700 and the smaller at x equals to 350. What's notable is the similarity of the two patterns, the solid wedge at the lower left, the salt and pepper cone at the upper left, the series of horizontal stripes which correspond to Zellberger's ultimately periodic sequences.
Hey Ten, you want to play a game?
Sure, why not?
Okay, let me teach you.